In this lesson, we'll go over doubling time and half-life. So what we'll do is we'll understand and calculate doubling time, and we'll understand and calculate half-life. So doubling time is the time required for a given amount to double. This is an example of exponential growth where our amount is doubling. The formula is given as our new value is equal to our initial value times 2 raised to the t little t divided by the doubling time. Notice this entire expression is the exponent of 2. So initial is the starting value, t is the time that we're given, and it should correspond to doubling time, and t double is the time it takes to double. And so what I mean that little t should correspond to the doubling time, like let's say the doubling time is in days, the time that we're counting should be in days. Or if the doubling time is in years, the time that we're counting should be in years. So example 1, the current world population is estimated to be 7.8 billion. Use a doubling time of 61 years to determine the population in 2050, 2075, and year 3000. Round to the nearest billion. And what we'll do is we'll express our answers in billions of dollars. Okay. So taking this apart, we have a starting value of 7.8 billion. We have a doubling time of 61 years, so this would be t double. And then the little t that we're going to use for each is going to vary depending on what we're calculating. So let's say A is 2050. If the current world population, this should have said 2020, is 7.8 billion, if we're looking at year 2050, this means that our little t is equal to 30 years. Okay, so since we're going to express our answer in billions of dollars, you can just use 7.8 if you want, and then round that number to the nearest billion. So plugging this into the formula, our new value, or our value in 2050, is equal to our initial value, so 7.8 billion, times 2 raised to the 30 divided by 61. Okay, now if you're going to put this into your calculator, the Casio is usually pretty friendly, but when you put this into the Texas Instruments, you do 7.8 parentheses, do the caret, another set of parentheses, and close it out. So your entire exponent has to be in parentheses here when you're doing this problem. And so I'm going to plug it in. These numbers get big, which is why I'm encouraging you to write them in billions of dollars. And I come out with like 10.96 something, so this would be about 11 billion. Okay. For the next one, part B, let's say, is the year 2075. There it is, 2020 population. So 2075, so we're using t as 55 years, okay, because we're going from 2020 to 2075. So you don't use the value before, you use what you're given in terms of time. So if we plug this in, we'd have our value in 2075 is equal to our starting value of 7.8 times 2 raised to the 55 over 61. Again, be careful with your parentheses here. If you're having trouble putting this into the calculator, as always, let me know and I'll be happy to take a look at what you're entering. So we get 14.57, so to the nearest billion would be 15 billion. If you're writing out 7.8 billion all the way, your calculator is probably giving you the answer in scientific notation, so make sure you put it into standard notation and then round from there. Okay? And then for part C, in the year 3000, that would give us that our time is equal to 80 years. Okay. And so in this case, we would take our new value in the year 3000. It's weird to say, 7.8 times 2 raised to the 80 over 61. Which gives us 19.35, so to the nearest billion would be 19 billion here. Okay. Next, talking about half-life is the time required for an amount to decrease by half. So this is an example of exponential decay. The formula is very similar, where our new value with half-life is initial times 1/2 raised to the t over t half in this case. And again, time should correspond to half-life. So if your half-life is given in days, the time that you're calculating should be in days, so on and so forth. Okay. So example 1, the half-life of carbon-14 is 5,700 years. So carbon-14 is used in what we know as carbon dating or dating radioactive material. If you start with 1,000 grams of carbon-14, how much will remain after 2 years? Round to the hundredths place. So we have our half-life, and we have our initial value, and we have our time is 2 years. So all we have to do is plug this into the formula. So 1,000 grams of 1/2 raised to this would be 2 over 5,700. Okay, and again, if you're plugging this into a calculator, I'm going to write it. Make sure you type it in as it's written in green so that you get the correct answer. Okay, and so I'm getting, this would come out 999.756. So if I round to the hundredths, the 6 rounds the 5 up. So my final answer is 999.76 grams, which makes sense. It doesn't decrease by a whole lot. It takes 5,700 years to reduce by half, which would be 500 grams from our starting amount. And so for only calculating 2 years, it doesn't go down by very much. Thank you for watching. If you have any questions, please feel free to reach out to me.